Okay, we're going to continue on here, chapter 2. We've been talking about measurements, units last time. Obviously, we talked about the importance of whenever we take a measurement, there should always be a number and a unit associated with it. Remember that a number by itself is pretty much useless as it gives no reference as to what that number represents. We talked about some different SI units. Remember, there's sort of the English units that we use. There's also the metric units that pretty much everybody else uses. And remember, the SI unit, which is sort of a version of the metric system, is really used in chemistry and science. And it's also important to understand, again, what those units represent in terms of what type of measurement. So again, if you say you got 50 grams, you're not going to say that's my volume because grams is, again, a mass versus 50 milliliters, where milliliters obviously is a volume versus a mass. So that is what we talked about. We also talked about the idea of volume, and one way you could get the volume is length times width times height, which if they were all measured in centimeters, for example, each of these are length measurements, but when you take those guys all multiplied together, we do get something like a cubic centimeter, which actually is a volume. So a cubic centimeter is the same as a milliliter, and those are units of volume. While again, each of the individual sort of measurements there, like you'll do today in lab, centimeters, 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 those are all length measurements. But when you multiply them together, you get a volume. One important or a couple important volume ones, cubic centimeter is the same as a milliliter. And there's 1,000 milliliters in 1 liter. Those are some very common ones. We also talked about qualitative versus quantitative sort of observations. Qualitative, again, is really observations that don't involve any type of measurement, while a quantitative observation is really a measurement. So that involves measurements, values, units, something that you actually measured through, say, some type of experimentation. Um, we talked about writing numbers in scientific notation, which is n times 10 to the n. Remember that when you properly do that, that first number should be a number between 1 and 10. A reminder that it shouldn't be less than 1, nor should it be 10 or higher. It does need to be a number between 1 and 10 to properly write in scientific notation. And again, that number up here will be positive or negative, again, depending on which way that you have to move the decimal point to get yourself to a number between 1 and 10. A reminder that if it is sort of over 1, a large number, positive exponent, smaller than 1, a negative exponent. More importantly, what we were talking about at the very end there is actually using your calculator in scientific notation. And again, the important buttons that we talked about on your calculator, these again are your kind of big 3 exponent buttons that you typically see. Remember, if you have these, when you hit any of these buttons, it does represents the times 10 part. So when you do put that into your calculator, a reminder, you should not be using a multiplication button, no like second logs or anything crazy like that. We also talked about other important calculations, which is your negative button, which looks something like this. Remember, if you do have a negative exponent or something like that, do not use the subtract button. Make sure that you do use the negative button when you do that. If you have sort of buttons here as your exponent buttons, a reminder that you pretty much the same thing. The only difference in order for the calculators to sort of do the math correctly. But other than that, it's pretty much the same deal. Any questions on any of that stuff that we did? I think we did some examples, right, using our exponent buttons. And again, if you're still not sure where your exponent button is, just bring it up and we'll be able to figure it out, I hope. All right, then let's continue on here, see what we've been talking about. So obviously here we were talking about scientific notation. So if we were going to turn these guys into scientific notation, we would again move our decimal here 1 place, 2 places to the left. And that would give us 5.68762 times 10 to the 2. We'll talk about it as we go through this chapter here, but all these numbers are significant, which means we do actually need to keep all the numbers when we write it in scientific notation. As we'll talk about, when you do write a number in scientific notation from, say, decimal form, you shouldn't lose any significant figures along the way. And we'll talk about how to count them here in just a bit. But you should not lose any going back and forth between them. Here we would need to go 1, 2, 3, 4, 5, and 6. And that will give us 7.72 times 10 to the minus 6, if I counted that right. Here, not written, but we would assume the decimal point is there. So we'll go 1, 2, 3, and 4 places, 1.25 times 10 to the 4th. Here, as we'll talk about, those zeros are not significant, so we actually can get rid of them here, and we should. And lastly, just one place there, and that'll give us 1.35 times 10 to the minus 1. A reminder that when we do write a number in scientific notation, as we talked about last time, all the numbers that come before the times 10 part are always significant. And one of the benefits of scientific notation, and as I might have mentioned last time, sometimes the only way to get it to the right number of significant figures is to write it in scientific notation, because you could kind of control how many significant figures you have. So again, if I had 3.2 times 10 to the 2, that would be 2 significant figures. If I had 3.20 times 10 to the 2, that would be 3. 3.200 times 10 to the 2, that would be 4. So you can really kind of control how many significant figures that you need by writing a number in scientific notation. As I also mentioned last time, you do not need to give your answer always in scientific notation, but you do need to give it to the right number of significant figures. So for me, you don't necessarily have to always give the answer in scientific notation. Any question on any of those there? All right, so just to kind of finish off this a little bit here, once again, we're going to go 1, 2, 3, 4, and 5. And that'll give us 4.25 times 10 to the 5th meters. And here, 1, 2, 3, 4, 5, 6, 7, I think. That's some really bad counting there, but I hope it's 7. 8 times 10 to the minus 7 here grams when we go that way. All right. So obviously you do need to be able to, as we talked about last time, write things in scientific notation, go for scientific notation back to digital notation or decimal form. And like I said last time, more importantly, how to properly punch it into your calculator. You usually have to battle in this class and in most chemistry classes that you take. So then let's talk about measurements and the uncertainty in measurements. And whenever you take any type of measurement, like you're going to be doing today, and I'll lab mainly today as well, for sure, there's always going to be some degree of uncertainty that's going to be there. And the degree of uncertainty really does depend on the piece of equipment that you're using. And it determines really how far you can take that reading or that measurement to the proper number of digits. So the first thing that you always want to do when you look or going to take a measurement is to actually look at the scale that's on the piece of equipment that you're using. You really want to figure out how far you could take these readings. So for example, if I had something like this, we'll do like a little ruler here, call these centimeters. And let's just say we wanted to sort of measure my arrow here. The first thing that you usually want to look at when you take a look at a scale, be it a ruler or graduated cylinder, beaker, whatever it may be, is you want to figure out what is the large markings mean. And usually the large markings will actually have numbers next to them. So here our large marking is 1, and our large marking here is 2, which means our large markings in this case represents 1 centimeter. The next thing that you want to figure out is, what does the smaller markings represent? The ones that really don't have numbers next to them in most cases. And you want to count how many you have. When we count how many of the smaller markings we have, we should always start counting past the last big marking. So in this case, 1 is the last big marking. And we want to start counting 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Thank you. And that means that we have basically 10 markings between 1 milliliter. And that means that each of our smaller markings in this case represents how much? Smaller markings represents 0.1 of a centimeter. If you're not sure, you take 1 divided by 10, basically. Yeah, and that'll give you 0.1. That means that this guy right here will be 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9. So when we take a measurement, there should really always be certain numbers that no matter who takes a look at it, everybody should agree upon. So we're looking at my arrow here. Everybody that takes a peek at this should agree that it is at least 1.4. And these are what are sort of considered our certain numbers. Now, we could clearly see that it is not exactly 1.4. It's not really 1.5 either. And this is where really our estimate comes into play. The uncertainty in this measurement comes into play about where it is. Now, I may look at it and go, I think it's like maybe a little further than halfway across there, a little further than half. So maybe I say, I think it's like 6. And then obviously I record my centimeters. Should always have units. This is what is known as the first uncertain number. And when we record a measurement like this, you should always record certain numbers plus that first uncertain number. And that is really what is referred to as significant figure. So significant figures is really when you do that, that is significant figures, basically. That means that this measurement that I just took has how many significant figures? It has 3 significant figures, yeah. The uncertain digit here is our last significant figure, which is 6. And in this case, for the most part, it's like plus or minus 1 of that number in the most cases. So you're basically saying, I think it's 1.46, but hey, maybe it's like 1.47, maybe it's like 1.45. It's somewhere in that ballpark, which if you look at the scale is pretty much where it's sitting, right? It's somewhere in that little area of our ruler. Now, you can also find the uncertainty in the measurement as well by taking the smallest markings and divide it by 2. If you take the smallest markings and divide it by 2, you will end up with plus or minus 0.05 centimeters, right? That basically means that sometimes people will record this as 1.46 centimeters plus or minus 0.05 centimeters. I have a feeling that you probably need to do that for lab. But for me, you don't necessarily have to do the plus or minus part of it, but for lab, you might have to do that. Okay. So that is basically how far you could take the reading to as well, by the way. It tells you basically 0.05 is 2 decimal places. You could take that reading to 2 decimal places based on that particular scale. Now, if we look at some other piece of equipment, for example, if we take a peek at a graduated cylinder here, professionally drawn, like a bad flask, and we'll do something like bad quality control at the plant as well. There we go. And we'll put a little bit of liquid right around where that tick mark is tilted there. It's good. By the way, when we do put a liquid into a glass container, you typically will see a curvature of the liquid, yeah, making like a U. That's known as the meniscus. And the reason that happens, we'll actually talk about in a later chapter, but really the reason it happens is the attractive forces between, say, the liquid and the glass are actually stronger than the attractive forces between the liquid in itself. So what happens by capillary action is that liquid that's next to the glass will start to rise because of the attractive forces, and it creates this sort of U that you will see, which is the meniscus. We always read in this particular type of meniscus from the bottom of the meniscus, because without that attractive force, those sides would come back down to where the middle is, basically, and that would give you the actual volume reading. So you should always read from the bottom of the meniscus. I would say pretty much most liquids will do that. The only one which you will not come across anymore because they've taken it out of labs because it's mercury and it's not so great for you, is mercury actually, for example, actually will do a meniscus in the opposite direction, mercury. And that's because the attractive forces between mercury and itself is greater than the attractive forces between mercury and the walls of the container, so it actually comes in on itself. In the case of mercury, you would actually read from the top of the meniscus because that's actually where the level would be. I would say pretty much most of the time, almost 100% of the time, that is what your meniscus is going to look like, kind of a U-shaped, and you always should read from the bottom of the meniscus. Do that. Sometimes it'll be easier to see than others, depending on the piece of glassware that you use. And sometimes it can be relatively hard to see. So we still want to do the same thing here. When we look at our scaling, we got a 10 and a 20. That looks like the large value is here is 10 milliliters. We also want to count how many dashes we got going on there between. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 10 dashes between 10 milliliters. 10 divided by 10 means that each of the small markings in this case is actually 1 milliliter. That means that this guy right about here would be 11, 12, 13, 14, 15, 16, 17, 18, 19. So when we take our bottom of the meniscus in this really badly drawn one here, everybody should take a look at it and should agree it is at least 15. So we would record 15. That would be my certain numbers. Once again, it is not exactly at 15, not exactly there at 16. So maybe in this case, you feel it's like halfway there between. We would record 0.5 milliliters. Once again, we can take our smallest marking and divide it by 2, gives us plus or minus 0.5 milliliters. That is 1 decimal place. That is how far we took the reading to. That is how you know, in case you're not sure how far you should take a reading to. You typically could take the reading to one more place to the right of the smallest marking. So if you could correctly identify what the smallest markings represent in terms of value, you could just divide it by 2 and I'll tell you how far you should take that reading to. So we'll do a little, if you want to include it there, 0.5 milliliters in this case. This would be our first uncertain number. That would mean in this case, this also has 3 significant figures, this particular number, the uncertain number there being obviously the 5, or the estimated digit being the 5. Question on that reading there. Bless you. Now, it is really important to always look at the scale because it is different. You may even be using 2 graduated cylinders, maybe you and your neighbor, and they actually have different markings on it because they were made by different people, right? So it does make a difference what piece of glassware that you're using. So let's just say that we had this. And we'll throw our liquid right about there. So now when we look at this, we got 10 and 20. So once again, our large markings is 10 milliliters. When we count up how many of our smaller markings we got going on, I got 1, 2, 3, 4, and 5 only. So actually in this case, if you take the 10 and divide it by 5, you will get 2 is the smallest markings. So in this case, our smallest markings are 2 milliliters. That would be 12, 14, 16, 18. Yeah. So now when I go to take a look at my reading right about here, I am between 14 and 16. What is between 14 and 16? It is 15 in this case. So the best that you could do in this case would be 15 milliliters. The reason for that is there's no good way to know exactly where 14 would end, where 15 would start in that little spot, because there's just too many numbers. We're able to make the assumption when it's just like one number, like, okay, halfway through is halfway to the next number. So you're able to kind of visually figure that out. Here, there's just too many numbers to know where it starts and where it ends. By the way, this number here would have how many significant figures? It would have 2 significant figures. The uncertain digit would be the 5 here, right? Which would be this guy. By the way, we could also do this here and it'll tell us the same thing, smallest marking divided by 2. is 1 milliliter, right? Plus or minus 1 milliliter. That's a whole number, which is where we took our reading to. So it does make a difference depending on the piece of equipment that you use as to how far you can take that reading. And you want to make sure that you always take a look at that particular scale. Any questions on that one there? Now, let's say we had the same ruler we were using before. Now, let's say we want to measure this line and it's going to be like dead on that line right there. And in this case here, it obviously is still the same large markings of 1 centimeter. Our small markings, there's 10 of them, which means, again, in this case, each of our small markings is 0.1 centimeters. So if we take a look at this, this again is 1.1, 1.2, 1.3, 1.4, 1.5. When I record this as my reading, I could record 1.4 centimeters, 1.40 centimeters, 1.40000000 centimeters. Feels like a lot of zeros, so I'm just going to cross that one out to start with. Is there a difference between those two measurements? Does it matter how you record it? The answer is yes. Sorry, probably wouldn't be asking that question. I imagine there is a reason for that, right? So let's just take a look at each of these measurements and sort of understand what is the meaning of the difference between them. Let's start with the 1.4. How many significant figures would this 1.4 have? It would have 2 significant figures. The uncertain number here is the 4. So when I record 1.4 in this particular case, what I'm saying basically is I think it's 1.4 centimeters, but maybe it's like 1.5, or maybe it's as low as 1.3, like that plus or minus of that uncertain digit up or down one. And that's basically saying when I look at this measurement that I just took here off of the scale, I think it's like somewhere in there, which is a big old area of uncertainty. Yeah, that's a lot of uncertainty happening in this particular case. If I take this measurement like this has how many significant figures? It does have 3 significant figures. The uncertain digit would be the 0 here. And when you take this measurement, what you're basically saying is, I think it's 1.40 centimeters, but maybe it's like 1.41, or maybe it's 1.39. That's like right about there in terms of my uncertainty, right? Based on this scale, the better measurement is 1.40. It's really what you see when you look at it. You should not do this one. And I know I shouldn't do this one because when I take the smallest markings here and I divide it by 2, I get plus or minus 0.05 centimeters, which is 2 decimal places. And that is how far I should take this reading. 1.40 centimeters plus or minus 0.05 centimeters, right? If you put everything in there. So I say this because a lot of times people, frankly, when they're in lab, it's amazing how many things always hit exactly on a number, exactly on a marking every single time. How did it happen a few hours ago? Everything hit exactly right on a number, exactly on the number. So if you lop off that 0 where you think like it's not that big of a deal, it really is that big deal. In this case, because of that scale, you actually have the ability to go out to 2 decimal places. So when you lop off that number, that 0 at the end, you're making your measurement pretty crappy, I guess is the way you can say that, a pretty crappy measurement. And it's not the proper measurement that you should be taking using that piece of equipment. You could take a much, much better measurement. So if you find yourself hitting exactly on a number, which does happen, or a marking or whatever it may be, you do have to include the zeros to maintain the proper number of significant figures when you take that measurement. Otherwise, you're pretty much making a crappy measurement and a wrong measurement. Any questions on measurements or how to properly take them? Yeah. All right. So as I mentioned before, that is essentially what significant figures are, and you should always, record all the certain numbers plus the uncertain numbers. This is also why certain pieces of equipment are much better to take, say, volume readings than others. Like a beaker is a pretty crappy piece of equipment to use to measure out volume because there's like only 2 markings or 3 markings. There's not a lot of markings. A graduated cylinder like you're going to use today has a lot more markings. You could take a much better volume measurement than you could in a beaker. People are sometimes surprised that they grab a beaker and go, I'm just going to measure out my, 50 milliliters in my beaker, and they fill it up to the 50 milliliters mark, and they're nowhere near it. The beaker is much wider opening, meniscus much harder to see exactly where the meniscus is, and you will be way off of 50. It's a really crappy way to do it. If you take something like graduated cylinder, much smaller opening, a lot more markings, you could really dial in exactly to that 50 milliliters. So it's really important to make sure you grab the right piece of equipment when you're trying to measure out something, because it may give you a much worse of a measurement if you don't. That brings us to some types of measurements like accuracy and precision. When we talk about accuracy, something being accurate, it basically is how close the value you got is to the true value. So for example, maybe you have an unknown and it has a true density value, like you might be doing today. Your number is really close to it, that's good. If it's really far away, it's not very accurate. Now, accuracy is different than precision. Precision refers to how close a set of numbers are to themselves. We usually think about accuracy as telling us how close something is. So for example, we oftentimes will calculate something like percent error when we talk about accuracy. And usually you want a very low percent error, which means you're pretty close to the true value. When we talk about precision, a lot of times we do something like standard deviation or percent deviation. We use precision a lot in labs, do experiments, do multiple trials of the same experiment, right? And we're using a lot of times for, is this like reproducible? Like, can we get the same answer every single time? Which is why we do a lot of trials. We also try to do it for accuracy as well and get the right answer. So the classic example is the throwing the darts at the bullseye, right? Dartboard. Goal is to get the guy in the middle there, right? The bullseye. So I take my darts, I throw them. I throw here, I hit over here, I hit over here. Am I very accurate? I am not. I hope I didn't hit anybody when I missed the dartboard. Am I very precise? Not so great either. So I gather up my darts, a little bit of my pride, and I go, hey, why don't we do a little double or nothing action here in a friendly non-wager gambling type situation. And I take my darts and I throw them again, and I go boom, boom, boom. Am I accurate? Am I precise? I'm precisely not accurate, yes? And that means that you could like screw up and do the same mess up every single time and get the same wrong answer, right? So like you add the wrong reagent every single time, but do it the wrong way every single time. You could be very precise. You could get the same answer every single time, and it could be very, very wrong because you're actually doing it wrong every single time. So again, there is a difference between precision and accuracy. I go triple or nothing in this case. Gather up my darts and I throw them and I go boom, boom, and boom. Am I accurate? Am I precise? I probably hustled you as well, which is not a good thing, but that is true. And that's really what you're shooting for if you do experiments, right? You want to be accurate, right? You want to get the right answer or whatever you're looking for, but you also want to be precise. You want to be able to reproduce your results, right, every time. So in the laboratory, we do try to aim for being both accurate and precise so that we have got the right answer and also can show that it is reproducible. Any questions on the difference between accuracy and precision? All right, so take a moment here. What is the right reading based off of this? The big numbers go with the bigger lines to the left. Okay, so let's take a look. So this big marking here is our 2, and this big marking here is our 3. So once again, our large marking is 1 centimeter, I think. We count up the little dots, starting with this dot right there and going all the way to the 3 marking, we got 10 marks. which means each of the smallest markings here is going to be 0.1 centimeters. So obviously that's going to be 2. 2.1, 2.2. This big mark is going to be 2.5, 2.6, 2.7. So it's at least 2.6. If we're not sure, we could simply do our little division here, and we know we should go plus or minus 0.05 centimeters, which means we should take it to 2 decimal places, right, based off of that. And that means it's not exactly there, so it looks like they might have went with a 9 and plus or minus 0.05 centimeters there. So it looks like maybe D looks like a winner in this case. Yeah. Any questions on that? Again, we would not lay up 2.6 as we have the ability again to go to 2 decimal places here. So we do need to keep those 2 decimal places. Any questions on that one? All right, so take a look at this one here and see what you come up with. Again, this is going to be 9. This big marking over here is going to be 10. So our big difference there in our large markings is going to be 1 centimeter. If we count the dots again, starting with this dot right there, we're going to have 10 dots, which means it's going to be 0.1 centimeters. And really, we could get to the right answer simply by just dividing by 2, actually, in this case. And that will give us 0.05 centimeters plus or minus. Clearly, that tells us we should take it to 2 decimal places. But if we really look at this here, that marking right there is 9.1, and that is 9. That means we're between that, so we got to be less than 9.1. So it looks like it's going to be that situation right there, 9.02 plus or minus 0.05. It is not 9.005 because we cannot go to 3 decimal places. Again, based off of this, we could only go to a maximum of 2 decimal places. Any questions on that one there? Now, again, as we talked about, sometimes we do use different pieces of glassware. So once again, if we take a look at this, which is a graduated cylinder, we're going to read from the bottom of the meniscus. We have 30 and 40. So our large markings on this guy going to be 10 milliliters. Starting to count here and continuing up to our 40 mark, there are 10 markings, which means that each of our small markings here are going to be 1 milliliter. And that would make that 31, 32, 33, 34, 35, 36, and 37, which is not 36, but 37. And that makes like we are somewhere between 36 and 37. We also know that if I divide this by 2, I should end up with a plus or minus 0.5 milliliters, which means my reading should go to 1 decimal place. So if you do nothing, not more with that plus or minus, is just divide it by 2 and figure out how far you should take your reading to, which is typically 1 more place to the right of the smallest marking. So they went with about an 8 there. So it was a little bit more than half they felt between the 2 markings. So it was 36.8. That would have how many significant figures? 3. The uncertain number would be 8. Is the uncertain number always the last number written? The answer is no. This is the last significant figure written, but not always the last number written. So 9 times out of 10, it happens to be the last number written, but is not always the last number written, that uncertainty or that estimated digit. But it should always be, as we'll talk about, the last significant figure that's in that particular number that you have. All right. Another piece of equipment that we'll use a lot throughout the semester here and as you go through chemistry, this is actually what's known as a burette. And a burette was used for titrations. We actually fill the burette from the top here, put a funnel on it or something, fill it up, and it actually will drip out the liquid from the bottom in this particular case. And burettes are a little bit different in terms of how their scale is. Kind of hard to see on this picture, but the very top is actually 0, and then it's like 1, and then it's 2, and so forth. It actually increases as you go down. And when we use a burette, we should always actually take 2 readings when we use it. Typically, when you use a burette, you take a initial reading as to where the liquid is in the actual burette, and then you usually will take a final reading. Although that looks like an IF. So you take an initial and a final reading. Is usually when you use some type of burette, you always take 2 readings. And the difference between those two is actually the volume of the liquid you added is your final volume minus your initial volume. So what that means is if we take something like that little scale there, and that's 0, that's 1, and that's 2. If you find your liquid sitting right about here, that's actually 1 point something, not 2 point something. So it's very important that you take a proper reading. Also, a lot of times these come as 50 milliliters or like 25 milliliters. And sometimes when people fill it to the top, they'll record it as like 50 or 25, the whole volume basically when they're at 0. You should never do that. You should actually record the actual number where the liquid's at. So in this particular case, if we zoomed in on this guy here, for example, this is 29, this is 28. The difference between those is 1 milliliter is our large marking. There's actually 10 dashes starting here going all the way down. That means that each of the smaller dashes is 0.1 milliliters. That means if I divide this by 2, that's a plus or minus 0.05 milliliters is how far I could take the reading. So when I use this burette right here, I could take the reading to how many decimal places? 2 decimal places, right? 0.05, basically take it to 2 decimal places. Typically speaking, 1 more place to the right of the smallest marking is what you could do. So for example, here, we could see that this is 28.5, 0.6, 0.7, 0.8, and so forth. So they take it here to 28.85, 2 decimal places, right? Uncertain number here is the 5 in this case, right? And that is the proper reading. On most burettes, I would say that's usually the scale. Usually you take it to 2 decimal places, but not always. Again, if it's made by somebody else, maybe you don't take it to 2 decimal places, but usually do. That includes if you actually filled it up all the way to the brim there to 0, you will record 0.00 milliliters if you had to record it properly. And again, we take a final and initial reading when we use a burette and we subtract the 2, and that will tell us how much we actually added in terms of the liquid. Obviously, if you started at 0, whatever your final reading is how much you added, right? So if you took like 22 and 22 minus 0 would give you 22 milliliters you added in there. But if I started my titration, for example, at 5 milliliters and ended at 20, I put in how much volume? If I started at 5 and ended at 20. I put in 15 milliliters. Yeah. So again, final minus initial will tell us how much we put in there. All right. So why don't you take a reading on this one, this burette, and see what you come up with here. Okay, so let's take a look. So this is 20, that's 30. So our large markings are definitely 10 milliliters. I'll come down here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings between. That means each of my small markings in this case is actually going to be 1 milliliter. That means that I could take this to how many decimal places? Three. I could actually take it to 1 decimal place. If I divide that by 2, that's plus or minus 0.5 milliliters, which is 1 decimal place. So in this case, remember it increases as we come down. So that's going to be 22 point something. So 22 with 1 decimal place looks like it is just this guy. It should be the right one here. So they feel it's exactly on the 22 marking. That is why, again, they recorded 22.0. Would it be okay to record just 22? It would not. Again, we would be making it a much worse measurement than it should be. 22.0 has how many significant figures? 3. And if I just recorded 22, it would have, once again, the uncertain number here with the 22 would be 2, right? Uncertain number with 22.0 would be 0, right? So much more uncertainty, right, by dropping out that 0 than the other, and then keeping it in there, which you should keep. I thought I heard a knock too. It's probably the person next door banging on the board. So let me just bother them next door. Hopefully they don't answer, I hope. All right. Any questions on measurements or how to properly take measurements? All right, so we've been talking about significant figures. So let's again officially make sure we understand the rules for significant figures and how we identify how many significant figures there are in numbers. Any non-zero are always going to be significant. So when we are counting significant figures, we always want to start left to right. We always want to start counting when we hit the very first non-zero. So left to right, very first non-zero, that is where you should start counting your significant figures. So clearly here at 1, 2, 5, 9, that is our first significant figure. They're all non-zeros. So this guy would have 4 significant figures. Zeros, there's 3 different types of zeros that we come across, and those are usually the ones that give people a little bit of trouble when they're trying to figure out significant figures. The first type of zero is considered a leading zero, and these are all the zeros that come before you hit that very first non-zero number. So all the zeros before you hit the non-zero number. Those are not going to be significant. So in the case of this guy here, none of these zeros are significant. We're not going to start counting until we hit the 4 at that case. And at that 4 and the 9 are both non-zeros, which means that this would have 2 significant figures. There's also zeros that are trapped between 2 non-zeros, and those are going to be significant as well. And in this case, we would start counting at the 5. These guys are trapped, which makes them significant, and we will hit the 4 there as well. So that would give us 4 significant figures. The one that probably gives people the most difficulty is the zeros that come at the end. They're sometimes referred to as trailing zeros. And trailing zeros may or may not be significant. And what determines whether or not they're significant is there a decimal point in the number? So the zeros at the end are significant if there is a decimal point in the number. Now, that decimal point in the number doesn't have to be sitting next to those zeros. It could be just anywhere in the actual number. And if you have a decimal point, any zero that comes at the end will be significant. So for example, here, I write my 600 like this, no decimal point written. It has only one significant figure, which would be this number right here. There's no decimal written, although we do assume that there is a decimal point when we turn something into scientific notation. In the case of significant figures, if it is not written, it's not there. Yeah, so we don't do any type of assumption like it should be there or not. So it does have to actually be written when we're doing significant figures. In the case of 600, written like this, this will now have 3 significant figures, as that decimal will make those zeros significant at the end. 600.0 would have how many significant figures? Everybody is significant here. Yeah, all 4 of them would be significant. We would start counting at the 6. All these zeros come at the end. There is a decimal point in that particular number. If I had a number like 0.000120040030000, how many significant figures in that crazy measurement? I don't know either. I was just writing numbers, to be honest with you. I don't know. There's something. I think there's more than one for sure, I would think. I don't know. Let me see. All right, let's take a look and let's dissect this craziness here. All right, so all these are leading zeros, as I have not hit a non-zero yet, so I'm not going to count. So I'm going to start counting right about there at number 1. So that's significant. That would be significant. These are trapped zeros, which makes them significant. The 4 is significant. It got me some more trapped zeros, which makes them significant. That's significant. How about the zeros at the end? Are they significant? No? No and yes. Those are both answers. One of them might be right. The answer is these zeros out here at the very end are significant because there's a decimal point right about there. Yeah, so they would be significant in this case. Significant, 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 significant. I don't even know how many that is. What's that? 1, 2, 3, 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Look at that. Not bad. So that extremely illustrates the point that sometimes people think like, hey, the zeros need to be like near the decimal point or something. They do not. So the decimal point just needs to be anywhere in that number, and be significant. After the decimal point is 0. Even though they come after a decimal point, but we haven't hit that first non-zero yet to start counting. So they would be classified as leading zeros rather than trailing zeros. Yeah. Questions on that there. Coming back to an earlier question, in the case of my numbers here, this number and this number, the uncertain digit in this number here on the left is which number? It is the 6, yeah? Not the last number written, yes? The uncertain digit on the guy on the right is that number, yeah, the 0. The one on the far right is that number. So this illustrates what I was saying a second ago, that the uncertain digit or the estimated digit may not always be the last digit that's written, but it should always be the very last significant figure that there is in that number. Like the 6 in the case of the first number is the last significant figure, and that would be our uncertain number, which obviously is a much crappier measurement, right, than the second one. That first one's basically saying, I think it's 600, but it might be 700 or, 500. That's a pretty big range of, I'm not really sure. The second one is saying, I think it's 600, but maybe it's like 601 or maybe it's like 599, something like that, right? So it's a much smaller area of error that could be in that particular measurement. So a much better. Any questions on any of those there? Now we talk about a couple of different types of numbers, and we really do come across a few different types of numbers along our way here. And type of number that from a measurement is considered a measured number. So it's considered a measured number. It essentially will have a certain number of significant figures associated with it because it was measured. There are certain numbers which are considered exact numbers, and exact numbers are pretty much found one of two ways. For example, if I have these pens on my desk, I'm not going to go do some type of experiment to figure out how many pens I have. I'm just going to simply count how many pens I have. So one way that you could come across something that's considered an exact number is some type of count. Classic example is apples in a barrel. You got some apples in a barrel. You're just going to count how many apples you got going on in there. Are pencils there? The other common way that we come across exact numbers in chemistry is through equalities. And these are all equalities, right? 1 inch is exactly 2.54 centimeters. 1 pound is 453.6. You do need to probably know along your journey here. 1 is 12 inches, 1 yard is 3 feet, and so forth here. These are equalities which are the two measurements that represent the same amount of something, but are on different units, right? Like if you have 100 pennies, it's the same amount of money if you had $1, right? They represent the same amount of money, but they are on different units. So if we come across anything that's considered a equality, is considered an exact number. So where does this come into play? It comes into play when you do calculations. So when we do calculations, we always want to give our answers to the proper number of significant figures. And when you come across an exact number in a calculation, you pretty much will ignore it. So you're not going to worry about an exact number in terms of the significant figures. And the reason for that is exact number could pretty much have as many significant figures as you want. It could have an unlimited number of significant figures. So when we do calculations that involve some type of conversion factor like this or equality, that's considered an exact number, we actually ignore it. And we oftentimes will more look at the measured number that has a specific number of significant figures to help us determine how many significant figures our answer should have. So speaking of that, let's take a look at a couple of examples here. I'm not sure. I guess we're going to sig figs on these, I think is what we're looking for. All right, sig figs on the first one's how many? It is 3. We would start counting at the 3 and take us all the way to the 4, which would be 3 significant figures. this guy would have? It is 4. So a reminder that when it is written in scientific notation, that tells you how many significant figures there are, which is before the times 10 part. By the way, when it is written, you shouldn't turn it into like a decimal number or something like that. By the way, when you do, you should have the same number of significant figures. But sometimes, for example, people will go, have something like this, and they'll turn it into like a number and go, okay, I wrote 3 numbers, so it has 3 significant figures. So you don't want to do that. By the way, it should only have 2. That's how I wrote it. You do just want to look at it in a sort of scientific notation form. Here, this is going to be 3. Yeah. Next one would have just 1. Again, no decimal written, so just 1 sig fig, which would be that 10. Lastly, here, this guy would have 4. We would start counting up to 9, and then we'd go all the way through. This 0 is going to be significant because of the decimal point that we have up there. So those 4 significant figures. Any questions on those there? Obviously, difference between measured and exact. Obviously, if you weigh somebody, that is a measurement, so that would be a measured value. Counting 8 apples would be exact. 1,000 grams in a kilogram is an exact number. So again, a quality. And the distance to Texas is 1,720 miles. That would definitely be measured. So let's talk a little bit about rounding. Normal rounding rules apply. So if it is like 5 or more where you need to round, the next number is 5 or more, we do round up. If the next number where you need to kind of stop is less than that, then we just drop the numbers. You don't want to do any crazy extreme roundings when you are rounding. So for example, say I had 12,000 here. And I want to do 3 significant figures. What should the answer be? See, I get that in my calculator and I look at my math. Significant figures. Is that 3 significant figures, by the way? When it's up there? How many significant figures is that number? Is 2. So I need to get it to 3. So how would I write 3 significant figures here? Scientific notation, 1.20 times 10 to the 1, 2, 3, 4, right? What about 12.0? Is that 3 significant figures? Is that okay? Well, if you're not sure, let me just give you a very simple example, which might make it clear to you. Let's say I owed you $12,000 and I go, hey, I'm going to pay you 3 significant figures. Here's 12 bucks. Am I going to make it out the door? Probably, you look like nice guys. Maybe you look nice. You let me out the door. No, there's a very big difference, right, in the meaning of 12, right, versus 12,000. So there's a very big difference in those two meanings. Although 12.0 is 3 significant figures, it is nowhere near the same value of what 12,000 should be. So although that is 3 significant figures, you never want to change the meaning of the number when you are rounding. So as was said here, we would want to write in scientific notation, once again, by doing it like this. That will give us 3 significant figures. Is there a way to write that number with 3 significant figures without scientific notation? The answer is no. And that was what I was saying earlier. Sometimes the only way to get the proper number of significant figures is to write it in scientific notation. You could write 12.0. That's not going to do it good for you. You do 120 point at the end. Also 3 significant figures, but 120 is better, but still not $12,000, right? So not the same meaning. So there's no way in decimal form that you could turn 12,000 into 3 significant figures and still maintain the proper meaning of that number without changing it into scientific notation. So keep that in mind. As I mentioned before, you don't have to always give the answer for me. I don't know about lab, but for me in scientific notation. You do have to give the right number of significant figures. And again, sometimes the only way to do that is scientific notation. Any questions on that? Super common error people make all the time is they're in such the crunch of I need to get the right number of significant figures, which you should, that they just kind of go extreme rounding on it just to get the right sig figs, but really do change the meaning of it. All right, so we want to round each of the two significant figures. So two significant figures here would take us to the 5. We're going to look at the 7 and see it's obviously above 5, so we're going to round up, and that would get us a 36 meters in this case. Yeah. Coming to the next one, second significant figure would be right about there, which means we'll look at the 2, which is less than 5. Do I just drop all the numbers and write 38? I don't. Again, it is two significant figures, but big difference between 38 and 3800 basically is what we got going on there. So you do still need the zeros, right? Or you could do a scientific notation on this one of 3.8 times 10 to the 3. Should I put a decimal point at the end of this one? I should not, because then that would have how many significant figures? We'd have 4. The uncertain number in this number is which number? It is 8. Yeah, 8. The uncertainty or the estimation is happening in this number. Coming to the next one, that's going to be a 6, which is our second. We are going to drop here 0.0026 liters. Here we do just drop the rest of them. We don't need to put the zeros, because if I put zeros at the end, what happens? They would then become significant, right? And it would be more than two significant figures. So again, adding zeros, sometimes you think, well, maybe I'll just keep adding zeros all the time. Not always the right thing to do either. So keep that in mind. Second, right about there, going to look at the 8. That obviously is going to round us up, and a 1.3 kilograms. Any questions on any of those there? So speaking about calculations, let's talk officially about when we do calculations, how we should end up in terms of significant figures, all that good stuff. There's really kind of 4 types of operations that you typically will do. You will multiply, divide, and you will add and subtract. So those are kind of grouped together. Adding and subtracting sort of one way, multiplying and dividing is sort of the other way that we look at. So when we look at multiplying and dividing, when you multiply or divide in a calculation, your answer should have the same number of significant figures as the number with the least number of sig figs. So you're looking at significant figures only when you're multiplying and dividing. And you should again end up with the exact same number of significant figures as whichever number is the least. The reason for that is it's your worst measurement, basically, right? Your least number of sig figs is your worst sort of measurement. So your calculation, your total measurement in all these cases is really only as good as your worst measurement. Kind of like that old saying, you're as good as the weakest link. Yeah, so your worst measurement is your weakest link in your calculation or whatever you're doing. So we the least. So for example, here, if we had 1.2 times 3.660. We are multiplying. That is significant figures. So that has 2 significant figures, right? This number has how many? 4 significant figures, as that 0 at the end is significant. That means my answer here should actually have 2 significant figures when I do it. And if I do this on my calculator, 1.2 times 3.660, that's going to give me a 4.392. That means technically I should go here, look at my 9, and I should round up, and we should end up at 4.4 as 2 significant figures. If I take 0.10 divided by 3.002, I am dividing. Top number has how many significant figures? It has 2. Yeah. 0 is significant, right? Because there's a decimal point in that number. Bottom number has 4 significant figures. So my answer, once again, should end up with 2 significant figures in this case. So 0.1 divided by 3.002 going to give me a 0.0333 0.31126 on my calculator. Two significant figures takes me to here. Looking at the 3 next to that one will give me 0.033 would be the proper number of significant figures. You could also write in scientific notation if you wanted to, as 3.3 to the minus 2 would work on that one. Question on multiplying. So multiplying or dividing, you're looking at significant figures only, and you're looking at the least number of significant figures is what your answer should have. When we add and subtract, it's a little bit different. When we add and subtract, we're actually looking at decimal places. And it is the number with the least number of decimal places is what your answer should have. So it is the least number of decimal places. So that's different than multiplying and dividing. Again, multiplying and dividing, we're looking at significant figures. Adding and subtracting, we are looking at decimal places, and it is the least number of decimal places. And it is the same reasoning. The least number of decimal places is frankly probably your worst measurement that you did. So it is the one that limits how good your overall calculation is. So if I had something like 1.1 plus 2.320 plus 1.00. I'll try it without the calculator. 2, 4, 2, 3, 4. My answer here should go to what? It should go to 4.4, as this has 1 decimal place. This has 3 decimal places. This has 2 decimal places. The smallest number of decimal places is 1, which means 4.4, which is 1 decimal place, is where my answer should go to. That has 1 decimal place. How many significant figures does it have? 2. And that's a different question, yeah? So you want to think about that in case you take that number and then multiply or divide with it, right? So you want to think about significant figures if you took that number along the way. What if I added numbers and one of them was a whole number? What should I take the answer to? I should take the answer to a whole number, right? A whole number, there are no decimal places, right? Is the smallest, so you would take it to a whole number if there happens not to be a decimal place there. So it is different, and people oftentimes get these things confused. So once again, multiplying, dividing significant figures, smallest, adding, subtracting decimal places, smallest. Questions on that? If you do it all together, you got to keep track of what you're doing. So for example, if I had 1.2 times 3.33 and I divide it by 0.100, where should I end up in terms of significant figures here? And by the way, should I be looking at significant figures here or decimal places? Which one should I be looking at? I should be looking at significant figures because on top I'm multiplying, right? And then I'm going to be dividing. So that's all sig figs. And if you were to do this, you technically would do the top part first, right? Which means that 1.2 is 2 significant figures, and you're going to times it by 3.33, which is 3 significant figures, which means when you get an answer for the top, it technically should be 2 significant figures, right? Then you're going to take that number on top, which technically should be 2 significant figures, and you're going to divide it by the bottom number, which has how many significant figures? It does have 3 significant figures. Those zeros are significant. Yeah. That means when you're all said and done, your answer should end up with 2 significant figures. Yeah, based on all that. So if you did all that, technically speaking, 1.2 times 3.33, you would get this for the top part, which would be 3.996, and you would divide it by 0.100. Would I round the top part to 2 significant figures at this point? The answer is no, and you probably shouldn't really round until you're kind of at the end of your calculation, especially if you're going to take the number and use it for something else. Sometimes people use guard digits, I think they call it. A couple extra digits than you need. Personally, I just keep the whole number in the calculator and just keep rolling with it. Some people will put a little a line up on top to remind you where you should be in terms of your significant figures. So you could do that if you want. But I personally would take the whole number here, then divide it by, not multiply, but divided by 0.1. And I will end up with 39.96. At this point, I know I should end up with two significant figures. Now I'm good to round, and I should end up at 40 with a little decimal point, perhaps, right? Because if I don't put the decimal point, I have how many significant figures? One, or you should do a little scientific notation in this case. Should I write 40.0? I should not, because then that would be three significant figures. Yeah, so you got to be really careful. Again, adding zero is not always a good thing in this particular case. Question on that there. By the way, you might also do a little combo action of everything here. So maybe you're doing that, and then we'll just add on to this since we sort of have the answer in front of us. Maybe we're adding 0.222 to this, for example, right? So now we would go through the same process, right? We do our multiplying first, we'll do our division. And at this point, I personally would still be rolling with this number and then add it to 0.222. So we would take 39.96 plus 0.222. That will give us something on the calculator of 40.182. At this point, I know that technically I should stop here, which is two significant figures, right? And that would give me how many decimal places? None, right? And I'm going to add something that technically has no decimal places to something that has three decimal places, which means my answer should actually end up with, at the very end here, of no decimal places, right? So we actually should end this guy, actually in this case, right back where we started in this particular example at 40. So if you do multiple steps along the way with calculations, you definitely don't want to round to the very end. You want to kind of keep track of it. Really sort of is that last step that sort of determines what you should be doing. So in this case, when I added the extra part to it, we did some multiplying and dividing first. So we're going to look at sig figs. But when we do that last addition step, we then have to switch from sig figs to decimal places and ended up with the right number of decimal places in this case. Any questions on any of that there? Why should you not round along the way? If you take a number, like do a calculation, get a number, take it, do another calculation, get a number, and keep on doing that. Every time you round, you're going to probably be moving yourself further and further away from the right answer. So it's a good idea. If you need to write a number, write a couple of extra digits. Again, they refer to it as the guard digits. If you want to put the little line up on top to remind you where you should be ending, you can, or you can just remember it, whatever you want to do. And then again, you should really just kind of clean everything up at the end once you're done with the last part of the calculation. And like I said before, personally, for me, most of the time, I just keep rolling with the number that's in my calculator until I kind of get to the end and then clean it up. Any questions on any of that there? All right, so take a moment and for each of these, round them off to the proper digits they should end up with. And a reminder, right, your calculator doesn't always give you the right significant figures or things in scientific notation, right? Okay, so let's take a look and see. So obviously, as I mentioned, your calculator will not always spit you out the right sig figs. And again, probably not scientific notation in a lot of cases, unless you have a program to do so in all cases. So here on the first one, we're multiplying. So we do want to look at significant figures, and it's the least. So that is three significant figures. That is two significant figures. That means we should end up right about there at two significant figures. We do need to look at the 7, so we're going to round up and a little 9.4 in that particular case. Question on that one? Coming here, we're dividing. So once again, we are looking still at significant figures. So first number has 4 significant figures. 1, 2, 3, which is creative, has 3 significant figures. That means that we are going to end up at 3 significant figures in this case. And that, looking at our number on our calculator, will take us to the 8. And we will round based off of the 2. And we'll end up at 0.0758. I think last time we also talked about the importance of keeping that 0, right, in those kind of smaller numbers before the decimal. Here we are adding, which means we are going to go to decimal places here. And once again, it is the least number of decimal places. That is 2 decimal places, 1 and 3 decimal places. Smallest is 1, which means this should round to 29.1, which again is 1 decimal place, but significant figure wise, it is 3 significant figures, right? So again, in case you need to take that number and multiply it or divide it, you want to go switch back to significant figures. Lastly here, subtracting, so decimal places 4, 1, and 4. So that looks like, no, that's the answer. Is 1 decimal place. So we're going to go actually to the 5 here, and we will round up because of the 8 that is next to it. Any questions on significant figures and calculations, how to take measurements, any of those things? Okay, it's a good place to stop.